Right now, as you're settling in to watch this video, something truly extraordinary is hurtling through the vast emptiness of our solar system. Something that originated from the depths of interstellar space, far beyond the reach of our sun's gravitational pull. This isn't your everyday asteroid or a chunk of cosmic debris tumbling aimlessly. This is 3I/ATLAS, the third confirmed interstellar visitor ever detected by humanity, a comet that has traveled for potentially millions of years across the void between stars before gracing our cosmic neighborhood. Discovered just a few months ago on July 1st, 2025, by the NASA-funded Asteroid Terrestrial Impact Last Alert System, ATLAS, telescope in Rio Hurtado, Chile, this icy wanderer is captivating astronomers worldwide. But what makes 3I/ATLAS so compelling isn't just its origins. It's the window it opens into the mysteries of the universe, the questions it raises about where it came from, and what it might reveal about other star systems. Stick with me through this deep dive, because by the end, you'll see why this comet could reshape our understanding of the cosmos, and I'll share some mind-blowing insights that might just keep you stargazing long after the credits roll. Let's start at the beginning, because the story of 3I/ATLAS is one of serendipitous discovery and rapid scientific mobilization. On that fateful day in July 2025, the ATLAS survey, designed primarily to spot potentially hazardous asteroids, picked up a faint, fast-moving object streaking through the constellation Sagittarius. At the time, it was about 4.5 astronomical units, AU, from the Sun, roughly 418 million miles, and moving at an astonishing 61 kilometers per second relative to our star. That's faster than most objects in our solar system, a telltale sign that this wasn't a homegrown comet or asteroid bound to the Sun's orbit. Within hours, astronomers at the Minor Planet Center analyzed the data and confirmed its hyperbolic trajectory, meaning it's not orbiting the Sun, but merely passing through on a one-way ticket back to interstellar space. Pre-discovery images dug up from archives, dating back to May 7th, 2025, showed it already displaying subtle activity, a faint coma or cloud of gas and dust, hinting at its cometary nature. By July 2nd, it earned its official designation, 3I/ATLAS, with the I standing for interstellar and the 3 marking it as the third of its kind, following 1I/Oumuamua in 2017 and 2I/Borisov in 2019. Imagine the excitement rippling through NASA's halls and observatories around the globe. This wasn't just another blip on the radar. It was a rare opportunity to study a piece of another star system up close. Unlike Oumuamua, which was asteroid-like and lacked a visible coma, or Borisov, which was more traditionally cometary, 3I/ATLAS arrived active and observable, giving scientists a treasure trove of data to unpack. As of September 22nd, 2025, observations continue pouring in from powerhouse telescopes like the Hubble Space Telescope, the James Webb Space Telescope, JWST, and even missions in our solar system like the Perseverance rover on Mars. But why does this matter to you, the viewer? Because interstellar objects like this are cosmic time capsules, carrying clues about the chemistry and conditions of distant stars. They challenge us to think bigger, about the billions of rogue planets, comets, and asteroids wandering the galaxy, ejected from their home systems by gravitational tugs or stellar explosions. If you're hooked already, keep watching. We're just scratching the surface, and the revelations about its composition and path will blow your mind. To truly appreciate 3I/ATLAS, we need to rewind and contextualize it within the history of interstellar discoveries. The first, Oumuamua, burst onto the scene in October 2017, detected by the Pan-STARRS telescope in Hawaii. It was a cigar-shaped oddity, about 800 feet long, tumbling end over end with no visible coma or tail, which sparked wild speculations, including Harvard astronomer Avi Loeb's theory that it might be an artificial probe from an extraterrestrial civilization. While most scientists dismiss that as unlikely, favoring a natural explanation like hydrogen outgassing for its unexpected acceleration, Oumuamua taught us that interstellar visitors could be stealthy and hard to study, as it was already outbound when spotted. Then came 2I/Borisov in August 2019, discovered by amateur astronomer Gennady Borisov. This one was unmistakably a comet, with a prominent tail and coma rich in carbon monoxide, suggesting it formed in a cold, distant region of its original star system, perhaps around a red dwarf star. Borisov was brighter and easier to observe, allowing detailed spectroscopic analysis that revealed similarities to our own solar system's comets, but with unique twists in its molecular makeup. Now fast forward to 2025, and 3I/ATLAS enters the stage as the third act in this interstellar trilogy. What sets it apart? For starters, its timing and visibility. Discovered inbound, we've had months to track it as it approaches perihelion, its closest point to the Sun, on October 29, 2025, at about 1.36 astronomical units, just inside Mars's orbit. That's roughly 126 million miles from the Sun, where the increasing heat will likely ramp up its activity, causing more ice to sublimate into gas and dust. As of now, its closest approach to Earth will be on December 19, 2025, at a safe 1.8 astronomical units, about 167 million miles, posing zero threat as confirmed by NASA's Planetary Defense Coordination Office. But the real thrill is in the observations. Hubble snapped images on July 21, 2025, when it was 277 million miles from Earth, estimating its nucleus size between 0.32 and 5.6 kilometers, though likely under 1 kilometer due to the obscuring coma. JWST followed up on August 6th, using its near-infrared spectrograph to detect carbon dioxide as the dominant gas, with traces of water vapor, carbon monoxide, and carbonyl sulfide. Ground-based telescopes like the Very Large Telescope in Chile have spotted cyanide and atomic nickel, emissions that are intensifying as it warms up. These details aren't just trivia. They paint a picture of a comet that's both familiar and alien. Its reddish coma, spanning up to 26,400 by 24,700 kilometers, suggests large dust grains, and a faint anti-solar tail is growing, pointing away from the Sun due to solar radiation pressure. Spectroscopically, it shows carbon chain depletion, meaning fewer complex organic molecules than some solar system comets, which could hint at its formation in a different stellar environment. Rotation estimates peg it at around 16 hours, with brightness variations indicating an irregular shape. As we watch this unfold, it's like witnessing a visitor from another world shedding its secrets in real time. If you're wondering how this compares to its predecessors, hang tight. We'll dive into that next, and trust me, the differences could unlock galactic mysteries you never imagined. Comparing 3I/ATLAS to Oumuamua and Borisov highlights how each interstellar visitor is a unique puzzle piece in understanding the galaxy's nomadic population. Oumuamua was enigmatic, no coma, extreme shape, and that puzzling non-gravitational acceleration without visible outgassing. Theories range from it being a fragment of a disrupted planet to a hydrogen iceberg, but its rapid departure limited data collection. Borisov, on the other hand, was a classic comet with a composition heavy in carbon monoxide, up to 30 times more than typical solar system comets, suggesting it came from a system with giant planets or a cool star. Its tail stretched millions of miles, and observations revealed diatomic carbon and other molecules, bridging the gap between our comets and those from afar. 3I/ATLAS fits somewhere in between. Active like Borisov, but with a more balanced composition, dominated by CO2 rather than CO, and showing water ice that's sublimating as it nears the Sun. Its hyperactivity at large distances, activity detected as far as 6.4 astronomical units out, mirrors some long-period comets in our Oort cloud, but its interstellar speed sets it apart. Polarimetric studies show high negative polarization in its coma, indicating a mix of icy and dark materials, perhaps from a parent body that experienced different radiation exposure in its home system. What's fascinating is the speculation it has sparked. Avi Loeb, ever the provocateur, published a paper in July 2025 suggesting 3I/ATLAS could be artificial, citing its ecliptic alignment and initial lack of certain chemicals. But the scientific community pushed back hard. Subsequent observations confirmed typical cometary gases, and experts like Chris Lintott and Daryl Seligman emphasized its natural behavior. NASA itself responded, stating it's a natural comet with no evidence of anything exotic. This debate underscores a key point. While we must remain open to extraordinary possibilities, extraordinary claims require extraordinary evidence. As you keep watching, we'll explore why these speculations arise and what they mean for SETI, search for extraterrestrial intelligence, because the truth might be even more profound than fiction. Speaking of NASA, their role in studying 3I/ATLAS has been nothing short of a masterclass in collaborative science. From the moment of discovery, the agency mobilized its arsenal of tools. The Deep Space Network, those massive 70-meter radio dishes in California, Spain, and Australia, has been tracking its position with pinpoint accuracy, though not for communication attempts, as some sensational stories claim, but for precise trajectory mapping. Radar systems like Goldstone have bounced signals off it to refine its size and rotation, revealing no anomalies beyond what's expected for a comet. Optical observations from Hubble and JWST have provided stunning visuals. Hubble's July 21st image shows a teardrop-shaped dust cocoon around the nucleus, while JWST's spectra peel back layers of its chemical makeup. But NASA's involvement goes deeper. The SPHEREX mission, a space telescope surveying the sky in infrared, observed 3I/ATLAS from August 7th to 15th, 2025, capturing data on its dust and gas emissions. Even Mars-based assets like the Perseverance and Curiosity rovers, along with orbiters, are set to watch it during its close approach to the red planet in October. The Europa Clipper, JUICE, Lucy, Psyche, Parker Solar Probe, and SOHO are all queued up for opportunistic glimpses. This multi-mission approach isn't just about gathering data, it's about building a comprehensive profile that could inform future interstellar studies. Artificial intelligence plays a role too, with machine learning algorithms sifting through terabytes of data to spot patterns in brightness fluctuations or gas emissions. These AI systems, honed on data sets from the James Webb Space Telescope, help detect subtle changes that might indicate the comet's internal structure or outgassing events. No unusual patterns suggesting anything artificial have been reported. Instead, the AI confirms it's behaving like a natural comet, with rhythmic brightness variations tied to its rotation. Why the urgency in NASA's response? Well, interstellar objects are rare, only 3 in over a century of systematic sky surveys, so each one is a golden opportunity. Unlike Oumuamua, which slipped away quickly, 3I/ATLAS's inbound path gave us lead time, allowing for planned observations that could yield breakthroughs in understanding exoplanetary systems. For instance, its carbon dioxide richness might suggest it formed in a warmer region of its original system, perhaps around a sun-like star. As we approach perihelion, expect more activity, a brighter tail, increased gas release, and possibly fragmentation if the nucleus is fragile. If you're intrigued by how NASA turns raw data into cosmic insights, stay tuned. We'll unpack the technology behind these observations and why it could pave the way for intercepting future visitors. Delving into the tech, NASA's Deep Space Network, DSN, is the backbone of deep space communication. But for 3I/ATLAS, it's been used for tracking rather than any contact protocols. The DSN's giant antennas can lock onto signals from billions of miles away, as they do with Voyager 1 and 2, now over 14 billion miles out. For the comet, they've provided high-precision ranging data, helping calculate its hyperbolic excess velocity of 58 kilometers per second, the speed it'll carry back into the galaxy. Goldstone's radar, capable of mapping asteroids from 20 million kilometers, has echoed pulses off 3I/ATLAS, confirming its size and shape without any frequency shifts indicating metallic structures or anomalies. Then there's optical laser tech, like the Deep Space Optical Communication System tested in 2023 on the Psyche mission, which demonstrated laser data transmission over vast distances. While not used for contact here, such systems could theoretically illuminate reflective surfaces on comets, revealing hidden details. In reality, for 3I/ATLAS, lasers from ground telescopes have aided in spectroscopy, identifying molecules like cyanide. AI integration is key. NASA's algorithms, trained on vast astronomical datasets, analyze these signals for patterns, repeating brightness dips from rotation or non-random gas bursts from outgassing. They've flagged nothing out of the ordinary, but the process showcases how AI accelerates discovery, spotting what humans might miss. This tech evolution ties into broader planetary defense. The U.S. Space Force and DARPA monitor such objects via protocols for unidentified space phenomena, but 3I/ATLAS triggered no alerts beyond standard notifications. It's no threat. Its minimum orbit intersection with Earth is 0.36 astronomical units, far safe. Yet it reminds us of the need for vigilance. NASA's NEO program scans for hazards, and this comet study refines those tools. Now let's address the elephant in the room. The speculations. A.V. Loeb's July 2025 paper posited 3I/ATLAS might be a probe based on early data like its path alignment and size. But as observations mounted, CO2, water, cyanide detections, the idea fizzled. NASA debunked it, affirming it's natural. This echoes past debates like the 1977 WOW signal or 1991 VG's odd orbit, both unexplained but likely natural. Even Voyager anomalies at the heliopause were glitches, not extraterrestrial. The real value of 3I/ATLAS lies in science. Its composition offers glimpses into distant chemistry, potentially from a system with habitable zones. As it nears perihelion, watch for peak brightness, around magnitude 12 to 13, visible in telescopes. Post-perihelion, in December 2025, it'll fade but yield data on tail evolution. Looking ahead, what if more interstellar objects arrive? With telescopes like Vera C. Rubin online, we might detect dozens yearly. Proposals for intercept missions, like Loeb's for a spacecraft to rendezvous, could become reality, sampling alien ices directly. In the end, 3I/ATLAS isn't about aliens, it's about connection. A wanderer from the stars reminding us we're part of a vast dynamic galaxy. It challenges isolation, sparking wonder. If this journey through its story has ignited your curiosity, subscribe for more cosmic adventures. The universe is full of surprises, and the next one might be just a discovery away. Thanks for watching to the end. You've unlocked the full picture of this interstellar marvel.